If you take a look at your new cheat sheet, you'll see that the very first section is titled Electrons and Light. We're going to be talking a lot about light today, and we're even going to go on a little field trip to visit a room that is much more dark than this room so I can show you a few things about how electrons can create light. But first we need to start off by just talking about remembering where electrons live. In our last unit, we focused on the middle of that guy, all right, the nucleus. Protons and neutrons were there. We're done with that. We're actually done with that for the rest of the school year, all right? That nuclear unit is pretty much all the focusing that we do on that nucleus. Chemically, the much more interesting area of an atom is going to be this outer area where electrons live. And we're going to start off with a new vocab word right away, because these circles, these pathways that electrons can exist on outside the nucleus, these guys are called, make sure you're writing everything I am, these guys are called orbitals. All of those green lines that I've drawn are referred to as orbitals. A circular pathway where electrons travel. What's the charge of my electrons? They're negative. So we're talking about these negative particles that are going to be rotating on these orbitals. Now, in some lectures that are coming up, we're going to be talking a lot about the very specific configurations of these electrons, but not today. Today is light day. Bless you. You just made the video. That sneeze will live in infamy. In order for electrons to create light, a very specific process happens. So what I'm going to do is focus just on this electron right here. So yes, there's all these other electrons that I've made up and drawn. We're going to focus on him. And I'm going to show you how this one electron that lives on the very first orbital in this case, I could pick any of them, but he lives on the very first orbital outside that nucleus, how he can create light, the light that we're about to go see in the dark room. First off, this electron lives here. This is his normal orbital, the normal spot that you would expect to find him if you were to go and look really closely at the electrons closest to the nucleus. This is where you would expect to find him. In order for him to begin the process to produce light, here's the first thing that has to happen. First, he needs to absorb energy. So I'm just going to kind of show an input of energy into that guy there. There he is. Ooh, we've charged him up with some energy. The moment that you do that, the electron becomes excited. Like, it's your birthday, excited. And when that electron becomes excited, watch what he's going to do. Watch what he's going to do. He's going to jump to the next orbital out. Look, he moved. He moved from here to there. Now he's there. This is the same electron. He's now in an orbital that he doesn't normally live in, and he's holding on to energy. He's excited. He's got this energy that we gave him from somewhere. We'll talk about where he can get that energy. But he got that energy from somewhere, and he jumped out to the next orbital out. He's excited. He's excited. He's holding this energy. But then he's going to return to the ground state. I'll give you a moment to write. The ground state refers back to where he started, back to where he usually lives. But watch what happens. When this electron returns back to the ground state, the energy that he was holding on to that was making him excited He's going to shed it. He's going to get rid of it. And when he does that, we see that energy as what we call a photon, which is light. I'm going to go over that process one more time because it's real easy to understand, so I want you to grasp it. Okay, so I'm an electron. This is my ground state, the spot where I normally live. Something comes along. There's 4 different ways we'll go over in just a moment. One of the 4 ways we're about to discuss zaps me with some energy. I absorb some energy. And what do I do when I absorb it? I get excited and I step outward to the next orbital out. I've moved further away from the nucleus. And now I've got energy. I'm holding energy. I'm holding energy that I don't normally have, and I'm so excited about it. But then what am I going to do? I'm going to go back. I'm going to return to the ground state. Now watch. Now while I'm returning to the ground state, I'm going to throw that energy off. How do we see that energy as? Light. A photon is the big, I'm in high school now, word for it. I'm going to give off a photon, which is light. Now, things like the color of that light and the brightness of that light and stuff like that, we're going to talk about that when we return from the dark room in a moment. But first, I want to go back to this step here. That step right there, that very first thing I drew was the moment that the electron absorbed energy to get that whole thing started. My electron's ability to absorb that energy is going to come from one of 4 places, and you're going to want to know these intimately. It can come from fluorescence. These are all ors. It can come from this, or this, or this, or this. It can come from a chemical reaction. It can come from electricity. Or it can come from heat. And before we move on to discuss further light theory, including things like color of light, I'd like to demonstrate some of these for you. You video people won't get to see those demonstrations, I'm sorry. Take a look at the back of your roadmap. No, I'm sorry, wow. Take a look at the top of your cheat sheet. Sorry. If you look at the top section of your cheat sheet, or rather, I guess it's kind of in the middle, you can see this table here that I'm going to try to teach off of or explain some basic vocabulary. What I have here is a very poorly drawn wavelength, all right? But, again, it serves our purpose. First, some basic vocab, all right? If something has a high frequency, what does that mean? In terms of waves, it'll be closer together, but if we have a high frequency, that would mean that it's happening often. You breathe at a very high frequency because you're always breathing. You're breathing, 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 breathing. All right? What's something you do at low frequency? Sneeze. That's exactly what I was thinking. It's so weird that you said that. We're on the same wavelength, right? Because it's stupid. Okay. Sneezing would be kind of more over here because it doesn't happen very often. Sneezing happens at a very low frequency. All right? So one of the things, just by not even assigning any meaning to this wavelength yet, just by looking at how my lines are close over here and far over here, I can already say that frequency increases this direction. All right. So for those of y'all that are writing what I'm writing, I pointed the arrow in the direction that it was getting faster. There's a much higher frequency. We're breathing over here. We're sneezing over there. Now, there's an inverse property, another vocab word, and it is wavelength. The length of the top of one wave to the top of another, the same location on the next, is the length between waves, the wavelength. That one's not brain surgery. But I want you to see that the wavelength increases the other direction. On the side where the frequency is high, the wavelength is very short. Do you see that? The distance from that wave to that wave, not very big. But on the side where the frequency is very low, our sneezing side, the wavelength is very large. So I can add another label here. I can say that wavelength increases the other way. Again, I'm pointing the arrow towards the increasing direction. And there's one more thing we want to apply to this, one more idea, and it's energy. Figuring out where more energy lives. Without looking at your cheat sheet, does anybody have a guess? Do you think there's more energy here or more energy here? The left side, you could even say where there's a higher frequency. You're right, to the left. So one more time, one more arrow. I'm going to say energy, and that increases the same direction that frequency does. And finally, in regards to like the different colors we saw when we went to the dark lab, I can throw the spectrum, which is the Roy G. Biv, the colors of the rainbow. I can throw the spectrum onto this. Now, mine's not, what I'm about to put won't match your cheat sheet perfectly. Your cheat sheet's right. You can see, look there, you can see that it's labeled for you, the colors. But for my people in digital world, it goes backwards. Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. And by looking at this picture, I can ask you 10 billion different questions. So let's go over a few of my 10 billion. Which color of the spectrum has the lowest energy? Red has the lowest energy because energy gets bigger this way. So that's where there's the most energy. So the least energy is there. Which has a higher wavelength, yellow or blue? Don't answer out loud. Let everybody think about it for a second. Which has a higher wavelength, yellow or blue? What's the answer? Yellow. Wavelength gets bigger this way. So yellow is going to be larger wavelengths. And if you think back to the midnight lab in there, that means that as I was turning those papers and getting the different colors, when it went yellow, it meant that I was increasing the wavelength. All right? What color has the highest frequency? Violet. And I want to just finish with one thought so that you see that this stuff really does apply to every light wave that you see. Violet down here does have the highest frequency. It also has the highest energy because energy and frequency are directly related to each other. But once upon a time, your mommy, yeah, your mommy, I'm bringing your mom into this. Your mom told you about this because your mom was a chemist once upon a time. You should have been taught to avoid all fire when you were a kid. But which fire did mom say to make sure you extra stayed away from? The blue fire. Some of y'all saw it as purple fire, but she was telling you that the fire that has this color is more dangerous than the fire that's orange or red, the more common colored fire. And she's absolutely right. The violet and blue fire has a lot more energy to it. And directly correlated to energy, like we talked about in our first unit, is heat. Therefore, that purple fire is a lot hotter than that red fire because of this idea alone. Any questions on light theory?